contribution to the study of usability and haptic feedback of encounter-type haptic displays. Virtual reality allows us to enter mesmerizing virtual worlds. And the recent interest of big companies in these technologies demands more and more sophisticated feedback within these virtual environments. There's the sense of sight. There's also the sense of audition. And what about the sense of touch? Well, research on haptics has been looking for solutions to this problem. We have different approximations to this, such as VR gloves that can render haptic feedback in the user's palm of the hand, and as well as other types of actuators, such as exoskeletons and force feedback devices, as we can see over here and here. And even we have also meter haptics approximations for rendering haptic feedback. Amongst all these solutions, there's another approximation, which are encounter-type haptic displays. But what are encounter-type haptic displays exactly? Well, I'm going to invite you to read along the definition with me, which says, in the context of human interaction with a virtual or remote environment, an encounter-type haptic display, or ETHD, is a device capable of placing a part of itself or in its entirety in an encounter location that allows users to have the sensation of voluntarily eliciting haptic feedback with that environment at a proper time and location. Okay, so the definition is over here, but what do we mean exactly? Well, as you can see over here in this picture, there's a robotic device that can actually provide a surface to be touched within a virtual environment. So users can actually encounter the surface, as you can see over here, and they can voluntarily engage and disengage contact with it. There are several features that compose an ETHD. Perhaps one of the most important is the actuator, which is the robotic device that places the surface display in an encounter location. The surface display being the actual surface that the users touch. The tracking system that acknowledges the position of both users and actuators and places them in the virtual environment. The haptic feedback that is elicited through contacting the surface display. The visual display for rendering the simulation environment. The workspace that refers to the space that is shared by both users and actuators in the physical environment. The simulation environment, which is the one that actually contextualizes the haptic feedback rendered by these devices. And the interaction between users, actuators, surface displays, and simulation environments. The context of this thesis is the Levibot project, which is a project funded by the French National Research Agency, and it's basically an ETHD which is used for automobile interior prototyping, as you can see over here. Basically, what this ETHD does is that it renders multi-texture haptic feedback for rendering different parts of the automobile cockpit. So designers can prototype different versions of this car cockpit in order to help the Renault company to prototype more faster and more cheaply virtual car cockpits. So now let's talk about the related work for ETHDs. We have a classification or a taxonomy for classifying the ETHD actuators into two main categories: grounded ETHDs, which consist on, for instance, industrial arms, which is the classical approach, is the approach that we often use in this thesis, which is just having an industrial robot that provides a surface to be touched in a virtual environment. But we have also fixed platforms, ETHDs, which are platforms, as you can see over here, which are fixed on the ground and can provide a haptic feedback, as we can see here in the work of Howard et al. We also have the ungrounded approach, which consists of ETHDs which are not attached to the ground, as we can see over here. For instance, we have unmanned air vehicles, such as drones. And for instance, here we have a drone that is caged and it holds a surface that can be manipulated in a virtual environment. We also have mobile platforms ETHDs, which are ETHDs that are capable of displacing within the workspace, and they can render different types of haptic feedback. In this case in particular, they hold pin-array surface display that can render different textures and different objects within the virtual environment. And we have also the wearable approach, which are actuators that are mounted over the user's hand without actually touching the user's palm, so they can give the sensation of actually engaging and disengaging contact with a surface, as we can see in the work of the Tanguy et al. We have different applications domains for ETHDs. Perhaps the most important is research, which is focused on actuator development for rendering haptic feedback within virtual environments, as we can see over here in this ungrounded mobile platform ETHD. We also have the medical approximation for rendering different surfaces, in this case for surgical operation simulator, where users can interact using an object over here. And for instance, in this case, in the work of Sujita et al., they can render this tissue using magnetic fluid, as we can see over here. We also have the entertainment approach for rendering haptic feedback for more ludic purposes, as we can see here in the work of Hoppe et al., where they can actually render objects that can be touched within fun applications. And of course, we have the industrial application, such as the work over here, which is by Posel et al., which is in the frame of the LobbyBot project for part prototyping. Concerning haptic feedback that can be elicited for with ETHDs, perhaps contact is the most prominent one. In this table over here, we have all the different haptic feedback that can be rendered with ETHDs. And on this side, we have all the ETHDs classified under the actuator taxonomy that we previously mentioned. And as you can see, contact is perhaps one of the most frequent feedback that has been used within these applications. And we also have the classification proposed by Lederman and Klatsky, which consists of haptic exploratory procedures, such as lateral motion for touching textures over here, as we can see. Pressure for rendering, for instance, in this case, musical instruments. As the user presses, it can render a sound. It's a novel approach for music. We have also contour following, which is, in this case, is using a haptic thimble surface display, which is basically a thimble that goes around the user's fingers, and it can lock into this position, so users can actually encounter that location, having the sensation of touching a contour, as we can see over here. We also have enclosure for rendering grasping sensations, as we can see here in these wearable ETHDs, which is actually not in contact with the user, but actually when users lower down their fingers, they enter in contact with a surface. We have also a static contact, which refers to temperature perception. So for instance, in this actuator by Araujo et al., they actually have an actuator that can render different temperatures. We also have unsupported holding, for instance, using the drone approach, for actually having the sensation of holding objects in virtual reality. We have power motion test for manipulating objects. And we have function test, as we can see over here, for actually operating a turntable, another work proposed by Araujo et al. So as we can see, haptic feedback can be leveraged by optimizing the ETHD surface display, because there are some limitations that we're going to further discuss, and we're further going to address in the following contributions. And in matters of interaction with ETHDs, what we can do is surface exploration, and what we mean by that is to touch a surface within a virtual environment, to explore it, to actually perceive its properties, perceive its shape, its textures, for instance. And we also have object manipulation within the context of ETHD, refers to actually grasping an object, releasing it. And we also have locomotion. We have ETHDs that are capable of rendering a surface to be stepped on. And we have also teleoperation, for instance, in this case, an application for medicine for remote palpation, as we can see. Despite all these applications, we need to take into account user safety, and it's going to be addressed in a further contribution. And also, interactions with ETHD, as you can see, largely depend on the actuators and surface displays of ETHDs, and we're going to further address this in the contributions that follow. So based on this related work review, we can say that there are 3 challenges that need to be addressed. Challenge 1 is usability, meaning how we can actually have a better performance when interacting with an ETHD, and if ETHDs are actually easy to use. Haptic feedback, concerning the types of haptic feedback that can be rendered within an ETHDs, and actuator performance, just to increase the performance for an ETHD to place the surface in a desired time and place. And the contributions addresses these research questions. For instance, the first contribution addresses user safety and interaction techniques research questions. The second contribution is focused on usability and haptic feedback challenges for interaction techniques design and large surface rendering. The third contribution addresses large surface rendering and multiple texture rendering. And the fourth contribution addresses object manipulation and control algorithms. So now let's begin with the first contribution, which is focused on improving user safety with ETHDs. As I mentioned before, this is purely focused on the usability challenge, addressing user safety and interaction techniques design. The objective of this contribution is to improve user safety when interacting with an ETHDs, and for this we created a design space for safety techniques for ETHDs, and based on this design space we conceived 80 safety techniques, which were later evaluated under the criteria related to users' immersion and perceived safety. But what exactly is a safety technique for ETSDs? Well, basically, safety techniques consist on providing visual feedback for telling the user that they're actually closer to encounter the robot in an involuntary fashion. As we can see over here, basically, when the users get close to the robot, there's going to be a feedback that is going to be displayed in different ways for telling information about the robot's proximity, its trajectory, and its configuration. We created this design space for conceiving the safety techniques, and we consider three main blocks. The block what actually focus on the information that we're going to give to the users. This can be either a warning or the system state. We have the block when for asking us when exactly we're going to display this visual feedback. It can be either suddenly, gradually, or permanently. And the block how for asking how exactly are we going to protect the user using this visual feedback. We can do this under several combinations, but you can find further details in the thesis manuscript. Basically, we created 18 safety techniques based on this design space that we cluster into 5 groups. The revealer groups, which are focused on rendering the ETZ as its configuration, is on the other side of the virtual environment. We also have trajectory beams for displaying the robot's trajectory. We have bounding elements that surround the robot, its trajectory, or the target position. We have blocker elements that interpose themselves between the users and the robot. And we have signal elements that display information about one of the properties of the robot or its trajectory. I'm going to show you a little bit of examples for the revealers group, for instance. As we can see, we have this technique, which is called full reveal, which consists of fully displaying the robot's contour. And we have also gradient reveal, which basically plays with the robot's transparency. As the user gets closer to the robot's mesh, the mesh is going to become more opaque. And as the user goes away from the robot, it's going to become more transparent. We have also trajectory beams that serve like some sort of loading bars for telling the users when the robot has finished its trajectory, as we can see over here. Bounding elements, as I mentioned before, that surround the robot. The blocker elements, such as the guardian angel, which tells users not to come close to the robot, or actually having a shield, for instance. And signal elements that just displays warnings, other types of, for instance, the position of the robot's actuator, as we can see here in the arrow technique. For evaluating these safety techniques, we consider 2 primary criteria concerning immersion and perceived safety, and secondary criteria that support the previous ones, which are visual clutter. For instance, if the visual feedback is actually cluttered in the virtual environment, is the visual feedback co-located with the actual robot's position? Are users becoming aware that there's a device on the other side of the head-mounted display? Ecological adaptability, meaning if the display or the design of the visual technique is actually fit to the virtual scenario. The mental workload, and if the users actually trust the safety technique. So we created a user study with the objective of studying the performance of our safety techniques under the criteria that I previously mentioned. And for this, we run an expert evaluation through a questionnaire with videos, such as the one we see here. For instance, this is the timer technique. That is a signal, that is part of the signal group. And it displays the elapsed time for getting from one position to another. And the collected data were basically the expert responses for grading our criteria, as I previously mentioned. And we considered 10 experts on virtuality and haptics. And then, based on the results, we ran a principal component analysis to find clusters of criteria. And we found 2 clusters. One we decided to call it immersion subscale, which groups immersion, visual clutter, ecological adaptability, and mental workload. And the other one, which groups perceived safety, co-location, device awareness, and user trust. And the results, as we can see over here, this axis means the safety subscale, and this one represents the immersion subscale. Overall, what we can see is that the gradient reveal techniques and full reveal techniques, which are techniques that actually display the robot, held best performance for both of these parameters. And also, as we can see over here, the rest of the techniques seem to be clustered, but we started to see something interesting over here. We are starting to see a diagonal over here, suggesting that there could be a trade-off between immersion and safety. Based on these results, we came up with design recommendations, such as for safety techniques for ETSDs, such as revealing the robot's actions whenever it's needed, creating informative feedback about what the robot is actually doing on the other side of the virtual environment. And of course, it is important to adapt the aesthetics to the use context. So in conclusion, we wanted to improve user safety when interacting with our ETHDs. We created a science space for safety techniques for ETHDs, and later a set of safety techniques, which were later evaluated on the immersion and perceived safety. And we learned that it's important to balance informative and aesthetic aspects for safety techniques, and also that techniques that display the ETHD actually yield a good performance for both immersion and perceived safety. Now let's talk about our second contribution, which is focused on interaction techniques for surface exploration. The research question that we are trying to address are interaction techniques designs and large surface rendering. The objective of this contribution was to study the design of interaction techniques, particularly for surface exploration, which I mentioned before was used to perceive the surface properties about as I mentioned before. We created a design space for the interaction techniques and later another set of interaction techniques, which were later evaluated under the task of surface exploration. What we mean by interaction techniques for ETHDs are basically interaction techniques that provide some sort of feedback about what can be touched or not in the virtual environment. And for instance, we propose here 5 techniques. The swipe technique, which is very interesting, that it basically uses control the safety technique and the displacement of the robot by just swiping over the contact area, which is represented by the green circle over there. We also propose other types of techniques, such as the clutching technique, which in this case is it uses a byte controller for actually triggering the technique, and this actually triggers a new surface selection. And as we can see, there's a timer that actually tells the user that the robot is actually rendering that surface, as we can see over here. We also have a drag technique, which performs quite similar to the clutch technique, but instead of using the controller, users only need to level up their finger and then lower it down for selecting a new surface to be touched. Sorry about that. So basically here, users are exploring the surface, and then they're just selecting a new surface that can be rendered with the ETHD. And there are also other interaction techniques, such as the bubble technique that works as some sort of steering wheel. So basically, the robot displays according to the vector between the center of the contact area and the point that is contacted by the user's finger. And as we can see, users can guide the ETHD from moving to one position to another. And we also have the follow technique that basically performs as basically acts as following the user's finger when they're leveling up the finger. And once they lower down the finger, they can select the contact area to be touched. So basically, what we created was a design space for exploring the different combinations and later for exploring these interaction techniques. And we consider first the input, which is the information that is provided to the interaction techniques for controlling them. We have 2 different variables. Either we can control it by a gesture or just by the controller input. We have movement control for actually manually displacing the ETHD, telling the ETHD to go to that desired position, or it can be being done in an automatic way. The displacement can be stepped, or it can be in an absolute straight shot. And contact, it can be whether users are in contact with ETHD while it's moving, or out of contact when the ETHD is moving. And based on these combinations, we created the interaction techniques that I mentioned you before. In order to evaluate these techniques, we studied the performance. We created another study with the objective of studying the performance of the interaction techniques under the task of large surface painting. So we created experimental procedures with 5 experimental blocks, 1 per technique, with 1 training trial for the users to get used to that technique, and then 3 experimental trials that consisted on surface painting, as I mentioned previously in the video. For this system setup, we use a Universal Robots 5 along with a prop that serves as a surface display, rendering the sensation of touching a large surface in a virtual environment, plus all the elements for detecting the user's position in the virtual environment. The data we collected was the lapse time for each trial and shape coloring percentage, meaning if the users actually managed to color all the shapes that were displayed, and also responses of a user experience questionnaire, which was based on the work of Shrep and Hassan Halero. Basically 8 questions that I'm going to further discuss under a population of 20 participants. Overall, the results were favorable for the clutch technique, which consists of having the controller for selecting another area to touch, but there were also good performances for other techniques. Concerning user experience features, we evaluated 7 factors over here: controllable, captivating, innovative, pleasant, motivating, and easy to learn. And also if techniques are fast. And we ran analysis variance and we found a significant effect for all the techniques concerning controllable, captivating, motivating, easier to learn, and fast. In conclusion, we studied the design of interaction techniques for surface exploration for ETHDs, and we created a design space for these interaction techniques, a set of interaction techniques which was later evaluated on the task of surface exploration. What we noticed is that users tend to favor techniques which actually are more easier to control, meaning that the more control they have over the technique, they're going to like it better. And actually, users actually like visual feedback that displays other information, such as the elapsed time for getting one point of another, which can be also connected to the first contribution where we actually included a timer, for instance. So now let's talk about the third contribution, which is focused on large multi-texture surface rendering, which is purely focused on the things that I mentioned that are just separated into 2 research questions. And basically for this, we created a novel approach for surface rendering with ETHDs, a use case scenario for contextualizing this approach, and later an evaluation for surface rendering using an ETHD. So what we propose is the entropy approach, which stands for encounter type rotating prop approach. And basically what we did here was to synchronize 3 important elements: the prop's displacement, the prop's rotation, as we can see over here, and also the user's hand displacement, in order to give the sensation of touching a large surface that is actually a round surface that is spinning just below the user's finger. For coupling this, we create an interaction technique that provides users with information about when they can start to touch, and then later, how can they display their finger in the virtual environment to have the haptic feedback sensation, and then how they can release contact with the surface. For this, we created a proof of concept, which was using again our universal robots number 5, plus the entropy approach, and the necessary elements for tracking the user and for displaying the virtual environment for contextualizing the haptic feedback rendered by Entropia. So this is our proof of concept, and basically what we can see over here is that there is an interaction technique that is actually telling us, guiding the user in the surface exploration procedure. And as we can see over here, there's the color code that is actually telling the users to touch and follow the contact area. And we can explore different textures over here, such as wood, paper, and leather. And this is the proof of concept scenario for multiple surface texture rendering. So for assessing the evaluation of this approach, for assessing the performance of this approach, basically we create a user study for studying large surface rendering using Entropia. And we consider to compare 2 different stimulus. The first stimulus is touch the ground truth, which is under the experimental prop over here, where users touch a large surface, guided by our safety technique, by our interaction technique, and 3 stimuli combination, such as the entropy approach, that is a translating and rotating round surface, as we can see over here, that is represented here and here. Comparing the ground truth against a translating round surface, and comparing the ground truth against a translating flat surface. The collected data were, at the end of each trial, we asked participants to evaluate the perceived similarity between the ground truth and one of the conditions in a 7-point Likert scale, with 1 being completely different and 7 to be a completely similar sensation. And at the end of the experiment, we asked evaluations to evaluate 3 important factors for differentiating the different stimuli, such as motion, speed, and curvature, under a 7-point Likert scale. And we considered a population of 12 participants. So results suggest that Entropia provided the closest sensation to touching the ground truth. And we also run analysis of variance and we found significant differences between all conditions, as we can see over here. And the translating rotating surface basically represents Entropia. So in conclusion, we studied large multi-texture surface rendering with ETHDs, and we created a novel approach for surface rendering, a use case scenario for contextualizing the different textures that we provide using Entropia, and the evaluation of Entropia for large surface rendering. And the insights that we got is that Entropia is actually can be a good approach for large surface rendering, and also parameters concerning prop rotation and translation speed should be adjusted for each user. And now let's move to our final contribution, which is focused on object manipulation with ETSDs. This contribution addresses object manipulation and control algorithms design. And the objective of this contribution was to improve object manipulation using an ETSDs. For this, we created a novel approach for object manipulation, illustrative scenarios that depict the key features of this novel approach, and evaluation of the control scheme that could be used for optimizing this approach. So we present you the Haptic Butler for VR, which is a robot that can provide a tangible object that can be detached from the robot surface, as we can see over here. So we have a butler that has a tray, a magnetic tray, that holds a tangible element that users can detach and attach to it. As we can see over here, basically Alfred maps the position of a tangible element, so users can actually proceed and manipulate it, and they can separate it from the surface. And once they want to just place it back, Alfred acts as an ETSD and provides the surface for placing the tangible element. For the setup, we used again our UR5 robot and the magnetic tray that I mentioned before, and the tangible element that can be detached from it, and users can actually proceed for manipulation. And in order to couple these interactions, we create an interaction technique, first considering the proper the pre-interaction phase, in which Alfred actually places itself in a location that could be optimized for object selection. Then we later proceed to the selection phase, where users proceed to select the object that they want to manipulate. Later, they can go to the manipulation phase, and then later they release the object in the surface. We have 3 illustrative scenarios for depicting Alfred's key features. The first is an assembly line scenario for depicting object creation and destruction, multiple object mapping for the VAR scenario, and a yard stacking scenario that I previously shown you for a virtual environment reconfiguration. So the assembly line scenario basically consists of having an object that can be rejected or accepted in an assembly line. And basically what we can do here is to simulate object destructions. As we can see, the object is going to be destroyed. And then we can also give the sensation of creating an object by just remapping the tangible element to a new element in the virtual environment. And we also have the bar scenario, where we can map the tangible element to multiple virtual objects in virtual reality, as we can see in this bar, where we can serve non-alcoholic cocktails. And basically what we are doing here is that we are just remapping the tangible element to a new bottle without alcohol, I guess. We run a performance study for assessing the different control schemes for ETSDs. I'm not going to dive into detail for these contributions. This is going to be further explained in the thesis manuscript. And basically, the evaluation was just to assess different points that can be reached within the virtual environment. We consider a population of 5 participants. Results were in favor of a snapping technique, which is basically going straight away to the target location. We have also other approaches based on following the user's hand that also yielded a good performance, and a least performance and a least reactive performance for a technique that actually waits until users pass a threshold before they can later snap to the target position. So the conclusion was to study object manipulation using an ETSD. We created a novel approach for object manipulation and illustrative scenarios for depicting its key features. And what we learned was that tangible attachment of an ETSD allows virtual environment reconfiguration. And then control approaches for ETSD should be focused directly on snapping to an interest point. In conclusion, what we did in this thesis was to study usability and haptic feedback for ETSDs. In the first contribution, we tried to improve user safety for ETSDs, and for this we created a design space for safety techniques for ETSDs, which were later evaluated under the criteria of immersion and perceived safety. And then another contribution focused on designing interaction techniques for surface exploration with ETSDs. We created another design space for a set of 5 interaction techniques, which were later evaluated under the task of large surface painting task. Now, concerning the part that is mostly focused on haptic feedback, the third contribution, we explore allowing large multi-texture surface rendering with ETSDs. And for this, we created Entropia, the approach for rendering large multi-texture surface, and we later use a user study for assessing the performance for rendering large surfaces. And finally, our Haptic Butler was introduced in our final contribution, which was an approach for object manipulation. And we later also evaluated the system performance for reaching different points in the virtual environment. As short-term perspectives, we can say that we can improve For instance, we can create multimodal feedback for user safety. We can provide auditive feedback or haptic feedback for telling the users that the robot is actually close to them. And we can adapt our safety techniques for other type of displays, such as augmented reality and mixed reality displays. The second contribution, we were focused on designing interaction techniques for surface exploration with ETSDs. And we can also explore interaction techniques for other types of ETSD actuators, when we can also explore interaction techniques for 3D surface exploration. In matters of entropia, we can integrate entropia to an ungrounded ETSDs to have a more unconstrained haptic feedback sensations. We can also further explore the influence of pressure and friction. And concerning our Haptic Butler, we can integrate multiple object rendering, meaning that our butler can actually provide more objects to be manipulated with. And also, we can be focused on multiple user interaction. Concerning long-term perspectives, we have 3 important axes. The first, usability axis. We can design interaction techniques for multiple user interaction. Concerning haptic feedback, we can advance towards the infinite surface haptic display. We can also integrate multiple surface displays. And concerning actuator performance, we can assess hybrid approaches between grounded and ungrounded ETSDs. We can finally go towards Sutherland's ultimate display, which was envisioned as being the display that can actually render all the sensations as in the real world, but in a virtual environment. This thesis yielded a series of publications that we already published on journals and conferences, and we have submitted other publications to our conferences. Thank you very much.